Hello everyone. Our project is prediction and classification for cancer factors. Um, we did this project to help doctors to diagnose and predict cancers. So in the first part, we did on genetic mutations level. So we did classification for genetic mutations based on clinical evidence. And in the part 2, we did on protein level about tumor prediction. And in the third part, we focus on a specific kind of cancer, cervical cancer, and we do images classification. And for the first part, we have the data sets that contains the genetic mutations and the clinical evidence to classify the mutations in 9 classes. And here is how we do data exploration. First, we do some basic data exploration in the genetic mutations part. We find the frequency in 9 classes and the genetic mutations distribution in 9 classes. And for the text part, clinical evidence part, we first find the text content distribution in 9 classes. And here is also the text count in 9 classes. And with the help of TF-IDF, we get the TF-IDF score for different genes in different classes. And then for some specific stop words, and with the help of word cloud, we get the word cloud of 9 classes for those specific words. So we can get a brief description of the dataset. And with the help of TF-IDF and with the help of GBM, we get the feature data of the clinical evidence text. So with the feature building part, we get the feature importance, and we set the feature fraction 80% and tagging fraction 80% and learning rate 5%. And then we get the feature importance graph, and we get the final classification for the data set, which is for each ID we predict the classification of all of them.
The second part of our project is to use the breast cancer Wisconsin dataset to analyze the relationship between molecule values and tumor status. This dataset contains many kinds of proteomics with their expression value from different patients, and different patients' clinical data, including hormone receptor status and vital status, and a list of PAM50 genes and corresponding proteins. The original study on this dataset is to perform the K-means clustering on the protein data to divide the breast cancer patients into subtypes and to find out the unique protein expression signature. To help doctors diagnose the cancer, we choose 3 sets of data to classify the status and predict it. Firstly, with the data of PAM50 proteomic molecules to predict tumor stage, which can help to understand the influence of these molecules. The second set contains estrogen receptor status, progesterone receptor status, and HER2 status, which are also used to predict the tumor stage to help doctors' diagnosis. Lastly, the status are used to predict the vital status to assess mortality risk of patients. During the prediction, we use several models to find out which one is the best at each case, and we use different sizes of training and predicting data to prevent the overfitting of the kernels. The models we use are support vector machine, Navier Bayes, and k-nearest neighbors, as well as the decision tree. For the support vector machine, we also use several different kernels for the prediction. And from the result, we can see that The tumor stage prediction by the molecule's value is quite accurate, especially for the support vector machine with the radial basis function kernel. And for the second part, we can see that the tumor stage is predicted perfectly for the SVM model. And thirdly, we can see that this is not a good model prediction because as the size of training data increase, the accuracy decrease. This may be because of the overfitting and the size of the dataset is not large enough. Well, the section 2 consists of 3 parts. The first one is to deal with the data. We will first read the data from the CSV file and then choose the columns we want. The second part is to choose the specific columns and to split the model from training part and decision part. Here we can decide the test size. And the third part is to use this data to train a model. From here we can see that we train a model with different kernels and different algorithms. For the other part of the section, we only change the columns we choose for the part, and we'll do the same modeling process. And the third part, we have the process like this.
For part 3, we want to do something with images. As you can see, I used a really big data set. It's about 80 gigabytes and consists of 1500 large cervix pictures. Trend data has already been classified into 3 types, type 1, type 2, and type 3. Test data is what we need to predict. Also, we use Google Cloud Platform due to the dataset is quite big. We build 1 master node and 5 sliver nodes. Each of them has 8 gigabytes memory and 250 gigabytes disk. Also, we use the Jupyter Notebook based on the Google server. Here is a warning. The following pictures may make you feel very disturbing, so you can choose not to look at the slides. Here are 3 types of cervix pictures, especially separately type 1, type 2, and type 3. We classify the images into 3 types according to the location of transformation zone in the pictures. It's really hard to explain what is transformation area. All you need to know here is transformation zone is such an area between 2 parts in the picture. We also use watershed algorithm to extract the features of the transformation zone from the picture because it's really hard to define such terminology. And the algorithm is really good at locating the boundaries in the images. For the model selection part, we use VGG-like model, the left one. It has only 7 layers and it's also a simplified version of VGG60 model. It takes less time to run the program compared with the VGG60 model. For the result part, actually VGG-like model didn't perform well in classifying these pictures. The accuracy is about 50%. It's not so good, just a little better than randomly guess. Here you can see type 1, type 2, type 3 is results for test data. Well, let me show you how the program runs now. As you can see, here is our Google Cloud Platform. Just click the Connect to connect to the instance with our browser. It's a little bit slow. Sorry. Oh, the internet connection is interrupted. Let's wait patiently. Hello, everyone. Welcome back. I'm sorry for the interrupt. Here you can see these are our instances. Just click the connect button to connect to the instance. Where you can see here is the uploaded test and trend data. Let's take a look at the trend data. Here are the pictures for trend data. Also, you can see how's the other folders look like. Let's continue with the Jupyter in our server. I use the port 3389, so we just copy and paste. As you can see, we get the Jupyter Notebook homepage. This is our main program. The most important part for this program is the watershed algorithm and the VGG-like model here. As you can see, VGG-like model has 7 layers. It's first layer, second layer, third layer, fourth, and plus another 3 public layers. Here we use in the trend model part, we use the kfolder function to split the trend data set into 3 parts, 2 for the trend and 1 for the test. Because we do this because the test data's exact result didn't provided by the provider, so we use this to calculate the accuracy of our prediction, and the result should be 50%. You can see here, this is our program's result. The program takes about 15 to 20 minutes to run, so it may take a lot of time to run the program, and I can show you here now. Okay, here is our project.